There we go. Let's go back. Homework 7 is not on Edline. Alright, so here we go. So I am going to redo what I just did so that now it's on. Alright, let's go through. Where's the pen? Critical values. So if you already wrote it, obviously you don't need to write it down again. So first thing, it can't be an endpoint. And then critical values, f prime of x equals 0 or f prime of x equals undefined. And another thing about critical values that people get confused, they are not always max or mins. So just because you have a critical value doesn't mean you have a maximum, doesn't mean you have a minimum. You do have to check your sign chart. Alright, so that's critical values. We then started talking about extreme value theorem. So you have a few theorems that you definitely want to make sure you remember. You have IVT. We said that that guarantees Y values. Okay, so anytime you see a statement like, explain why you are guaranteed that f of c equals 5, you're asked to guarantee a Y value. Then there's extreme value theorem, which is a little bit off from the others, guarantees an absolute, not just a max, an absolute max, and an absolute min. Not one or the other, but both. Okay? So, to start off, let's talk about what we need for it to happen. What do we need for f of x to be? F of x needs to be closed and continuous. Yep. And the continuity, actually I will put that on the closed interval, because some of you guys don't understand that. If my closed interval is from 1 to 5, but I have a vertical asymptote back at -2, then it doesn't matter, because it's not in the interval I'm looking at. Okay? Differentiability, should that be up there? So I'll just draw something. Actually, no, that argument doesn't necessarily work. I'm just going to say no. It's the only theorem you guys have that differentiability mattered. Mean value. Just remember it that way. Mean value theorem is the only one that differentiability mattered. IVT and EVT have the same exact thing. So logically, put your pen down at a point. Okay, you don't have to really draw it. And then it has to be continuous. So if you're drawing the graph, you would never pick it up ever again, right? So you go through, and you draw something. And it can look crazy as long as it's a function, so please don't swing in circles. Okay? So you go up, down, and you can even make a cusp. You can make a vertical tangent. But as long as it's continuous, can you mentally picture the fact that there had to have been a highest and there had to have been a lowest? The cusp and the vertical tangent didn't matter. But I could easily pick up my pen, and the second you pick it up, the theorem no longer works. You might have a max, you might have a min, they might be absolutes, but you're not guaranteed that it will 100% happen. Alright, so there are your two things, and then just making sure you understand guaranteed, an absolute, highest absolute max, and absolute min. You will 100% have a highest point and 100% have a lowest point. Things that you want to remember could be endpoints. And that was one of the things that gets tricky. If you don't remember that, you forget to check them, tend to get some problems wrong. So let's go through the steps of what we need to look at. And some of the steps you can move around. I usually start with things that I know you'll forget. So I start with these two things. I start with domain. If your domain has endpoints, because maybe the function is a semicircle, and the semicircle starts at a point, loops around, ends at a point. I'm not going to tell you the domain of a semicircle. You're going to have to figure that out for yourself. Therefore, it has closed endpoints. So we always check the domain. Other reasons why, you want to make sure you know if there's any discontinuity, we're going to cut that out of our sign chart. We're going to X those numbers out. So that's the first thing. Second thing, actually, let's not call it check. I'm going to actually have you find if endpoints, find the y values. And same thing. I only make people do that at the beginning because you usually forget at the end. So if you just kind of make the things happen that you know you'll forget, better chance that you won't forget them. Because if I say max or min, most of you will just automatically say, find what? Max or min of f. Find zeros? Find f prime, and then you'll tell me to make it equal to 0, and then you'll tell me to make it equal to undefined, and you'll tell me to do a sign chart. And you get all wrapped up in that really nice calculus math. A lot of you will never remember to go back and double check endpoints and double check your domain. That's why I put those first. Alright? So starting out with that. Then, number 3, find your critical values, right? Find f prime of x equal to 0, or f prime, or I forget if I use or and. Find both. Not just one or the other, both. I guess I should put an and for you guys then. And. Now I'm going to do my sign chart. Within domain. And here's where we cross out values not in domain. Alright, so once you know where your possibles are, you have possible maxes and possible mins. Number 5, use a table of y values to compare. So what I'm going to do is kind of simplify this. I'm going to take away the function part. I'm going to take away the first 3 steps. I'm just going to give you a sign chart, and we'll talk about what it means to do these last 2 things. So here's my sign chart. We're going to go from 2. We'll put 2 of those. 3, 5, 9. We'll say that the derivative here is 0. We'll say that the derivative here is undefined. We'll say the derivative here is 0. We'll say that that undefined is like that, and then I'll put my signs in. And then, actually, let me make this a minus also. And I'm actually going to copy that, and I'm going to do the same thing again in a second once I remember how to get a camera up here. Alright, so we got our little sign chart. And then I just made another one up here, and I will end up changing one little thing on that one. Alright, so there's my sign chart. So, what I would be looking at is, given this sign chart, I'm going to make it slightly smaller so I have a little bit more space. Let's say that we're going to do all of our extreme values, so maxes and mins. Okay. So when I look at this, is 2 going to be a max or a min? A maximum. So it's a maximum because you started at an endpoint and then you decreased. Does that make sense? And it has to be a maximum? Okay. The 0 there means we're flat. And then the decrease here, actually I should change my color. Let's try this again. We're flat. We're going down again. So 3, is that a max or a min? Neither. Neither. It actually is a point of inflection, but right now it's just going to be flat. Alright. Then undefined here, well, this is not crossed out. So there are only 3 options of what could happen. What are the only points that are undefined derivatives? Cusp, corner, vertical tangent, and then the last one would have been discontinuity. Well, it's not crossed out, so what do we cross out in our list of 4? Discontinuity. The sign goes from negative to positive. It goes down and bounces back up. Another one we can cross out. Vertical tangent, because vertical tangents increase and keep on going, or decrease and keep on going. So I want you to understand that those are pretty much the only options you have for that. But in having that option, I know for a fact that this is still a minimum. Does that make sense? Okay. Then we're going to go back up to a point. All right. And so this one here has to be a max. So let's say I wanted to know where the absolutes were. Okay. I want to know if you had any. Well then, make your table of values and see if any of them would be bigger or smaller. So when I look at these, I know that at 2 I have a max. At 9 I have a max. So actually, let me go in order. And in between, at 5, I have a min. So here I know I'm going to have a min. Here I know I have a max. Here I know I have a max. And how would I know which one's going to be the absolute? The y value. If this is -2, but this is -1, then this one's the absolute. Okay, so that's what I mean by table of values. It organizes the information better. But this one, if I do this, and I say, oh, never mind, 5's not part of the domain. There's a something's going on there. Could be removable, jump, vertical asymptote, which is an infinite. Could be any of those, oscillating, right? But I take that out. So now, as a result of taking that out, do I have a minimum here? No. But if you didn't remember to do that, does it look like I have a minimum here? Yeah, obviously, we just found it. So make sure you cross out values in the domain that aren't going to be part of the sign chart, and it makes you remember, oh, even though it went minus to plus, I can't use that point. Okay? Little things to help. All right. So increasing, decreasing. How do you know if a function is increasing? Positive sign chart on f prime. Negative is your decreasing. And then the only other thing I want to talk about is, what if they just ask you at x equal to 4 is f of x increasing? What if they just ask you that? Well then, I want to make sure you don't go crazy trying to make this complicated sign chart. Because if they ask you a specific value, do we remember what we do? We only do the specific value. So what if it was 0? It's not increasing? No. All right. What if it's 2? Yes, it is. What if it's -2? No. So one value in a derivative will tell you if you're increasing or decreasing. You don't need a full sign chart to do it. It's pretty much everything. Any questions that you guys have, looking at your notes, anything we feel like we did not go over? All right. So we got a good amount of time. Oh, I didn't end it. All right. So y equals sine of x to the x. So now you have a base that's an x and an exponent that's an x. And we talked about that before when we did derivatives. What do you need to do to make that work? Take the ln. So problem is you can't have an x to an x. So you got to get rid of one of the two. So we simplify it by taking the ln, makes the power come down and multiply. So on both sides we're taking an ln. Let me just make sure I remember what the question is. dy dx. All right. All right. So we good so far? So what else would we do? We would then get ln of y is equal to the ln of sine of x, but then that x I'm going to bring into the front. So I'm going to sneak that in. Are we good? All right. So now that I have it simplified, so I don't have a power to a power, are we good to take the derivative now? All right. So ln of y, the derivative would be 1 over u multiplied by the derivative of u, but that just is 1, and then multiplied by dy dx, which could also be considered the derivative of the inside. Ramsey, you're alive and awake. Barely. I can see. All right. Take a little walk around if you need. I think that's the only thing that keeps me awake, the fact that I stand. Alright, what rule do I need on the other side? Power? Product. Leave the first one, multiply by the derivative of the second. So, start me off with 1 over u, multiply by the derivative, which is the cosine. Please don't call it cosine. Alright, leave the first one, derivative of the second, plus, leave the second one, derivative of the first, which happens to just be the 1. Alright, so that looks good so far. Let's see. If I want this by itself, I would have to multiply y to this side, correct? Alright, so dy dx equals y. There's two terms, right? I'm going to put a big old bracket so I remember that. I'm going to clean this up a little bit. I'm going to write it x cosine of x over sine of x plus ln sine of x. So then I'm going to look at my answer choices and I say, man, why is that in there at all? So I got to get rid of y. Put in the original equation. So if I want to eliminate a variable, I'm going to need some type of substitution. Does everyone see I could use the original equation so that I won't have the variable y? So let's actually move that over to the next page so I have a little more space to write. Oh, no. That. Alright. There we go. So I'm going to put in y is equal to sine. Is it sine of x to the x? Was that correct? Alright. Does that match anything? No? So we're going to have to keep simplifying. Do any of them have a factor? So they do have some factors, right? So I feel like I'm going to be confident enough to leave my answer alone so far. Which one looks closest? E. Could this be E? Yes. Why? Ah, cosine over sine is equal to cotangent. Perfect. Yay. Are we good? Lottie? We're good? Awesome. Oh, did I freeze it? Let's see. Oh, I did. Alright, so mean value theorem. So, mean value theorem, what are the things you need for it to happen? You need the function to be closed. And I'm going to say the same thing as before. Continuous on the closed interval. That's the first thing. Actually, first two things. And be careful. You need f of x to be differentiable. No corner, cusp, vertical tangent, or discontinuity on the open interval. So what does that actually say to us? When I say on the open interval, what does that actually mean? Parentheses, true. Doesn't include the endpoints. Perfect. Alright, so those are the things. So then what you're going to find is that the instantaneous rate of change, so the derivative, will be the same as the average rate of change within open interval, meaning it can't be the endpoint. So to do a mean value theorem, to understand it, you're essentially, in terms of the algebraic analytic process, you're going to find a derivative. You're going to make it equal to the slope between the 2 points that they're talking about. Okay, so that's pretty much the analytic. What does it mean graphically? Okay, so we have this guy. I'm going to rewrite the same exact thing. So what does it mean in terms of a graph? Well, so in terms of a graph, when we look at a graph, what does the derivative find us? The slope of the graph at a point true. What's the special word I definitely need in there? What type of line? Tangent. Slope of the tangent line. Now, when we talk about this side, we don't call it a tangent line because it doesn't touch once. What's the other word? Slope of secant is when you touch twice. Two endpoints, connect them, that'll be a secant line. Okay, and we talked about the fact that your secant and your tangent lines might intersect the curve more, but we don't care about over there. We only care about at those points. Okay. How do I make two slopes be equal? I want these slopes to be equal. So what does it actually mean about the tangent line and the secant line? What happens when two slopes are equal? The two lines are parallel. So if I just draw a quick curve, right? If I go through and I connect, this is my secant, I connect them. If I can find where my tangent line will be parallel, and I think there's one about here, and maybe one around here. There's two, in this case, within the interval. Okay? Good? Awesome.